Hi students, hope everyone is fine and safe. It gives me immense pleasure to welcome you all to my new video, and today's video is about another interesting concept in microcontroller 8051. We're going to see memory organization of 8051, IO addressing and interrupts of 8051. And before starting this video, I would recommend you to go through the previous video, the architecture of 8051, so that you can understand all the concepts clearly with this memory organization. So we'll start with memory organization of 8051. So before going through this program memory and data memory, everyone know about ROM and as well as RAM, read-only memory and random access memory, right? And 8051, we have internal ROM of 4 KB, and we know that the internal RAM of 128 kilobytes, right? So ROM is always called as non-volatile memory, and so whatever programs which we have to store in microcontroller, right, it will be stored in ROM, read-only memory, right, because it is non-volatile, because program is going to be a set of instructions which is not going to change much. So those program instructions will be saved in ROM. Whereas RAM is in volatile memory, and where we will use it for data storage, right? That is the very basic information about ROM and RAM. And similarly in 8051 we have 4 kilobits of internal ROM and as well as 128 kilobytes of internal RAM, right? And both this RAM and ROM can be extended up to 64 kilobyte by using an external memory, right? And apart from it, we know that 8051 is an 8-bit controller, right? And we'll use 8 bits to access the memory location, right? And if it is 8 bits, totally how many memory locations is possible is 2 to the power of 8, which is normally 256 bytes. 256 bytes. And this 256 bytes can be segregated as upper 128 byte and lower 128 byte, right? And this is the normal split up for RAM in 8051, the memory allocation split up, right? So we will have 128 byte of internal ROM, right? And that is out of 256 we can separate it as upper 128 bytes and lower 128 bytes. Whereas the lower 128 bytes is where all the registers, the bit addressable memory, everything will be comes in this 128 bytes, right? Whereas the upper part, upper 128 bytes, we will have special function register. If you don't understand what is special function register, please go through the architecture video of 8051, right? So with this basic, we will now see how the memory is organized in 8051. Right? When you say program memory, all the programs will be stored in ROM, right? And whenever we say ROM in 8051, we have on-chip RAM, that is internal memory, as 4 kilobytes, which can be extended up to 64 KB, right? That is the external memory. Similarly, data memory, that is, this is RAM, right? So in order to save data, right, we will go for RAM. And this RAM, as I said, it can be split into upper 128 byte and lower 128 byte, right? Where the internal bytes, 128 bytes, that is the lower 128 bits is accessible, right? That is, we call it as internal RAM. And upper 128 byte is allocated for special function register. You can see that. And also we can also extend this RAM memory to a 64 kilobyte, right? This is the basic memory organization of 8051, right? Now we'll see how RAM memory is split. We know that right now upper 128 bit and lower 128 bit, right? So we consider this as a lower 128 bit, 128 kilobytes, and this is upper 128 kilobytes, right? As I said, the upper 128 kilobytes, right, it will be given as it will be allocated for special function registers, right? And the lower 128 bytes, you will have a lot of registers here, right? So you can see here the memory allocation, right? Everyone knows that hexadecimal hexadecimal representation, right? So the memory allocation you can see here for lower 128 byte, it starts from 00 and ends at 7F, right? And similarly, the upper 128 bit starts from 80F, 80H and ends at F of H. This is the memory allocation, right? And you can see here this 128 byte, it has been split into three different categories, right? That is, you have 32 kilobytes of register banks. You can see register banks, bank 0, bank 1, bank 2, bank 3, which starts from 00 to 1F, right? We have already seen in architecture how this register banks will be selected based upon those two inputs, based upon the values, right? And this register banks, right, you have totally 32 kilobytes, and then you have 16-bit addressable register, right? This is 16-bit addressable register, which is it's bit addressable. What is bit addressable? Bit addressable in the sense, right? Say for example, you have 8 bits, right? You have 8 bits, right? But you want to access only 2 bits to represent any particular representation. Then we can use this 2 bits alone. We don't want to worry about all these bits, right? That is called as bit addressable register, right? So you have 16-bit addressable register, 16-bit addressable register, right? That the memory location starts from 1F to 2F, right? And apart from it, you have 80 kilobytes of free registers, that is general purpose registers, right? You have 80 kilobytes of general purpose registers. This is how this total 128 bytes is splitted inside the internal ROM. Whereas the upper 128 bit, it is allocated for special function register, where the special function register address starts from 80 to F of H, right? So whenever we address the memory location 00 to 7F, it represents the internal RAM 128 bit, and whenever we represent the memory location 80H to F of H, then it refers to special function register, right? And we will see next video about the addressing modes, but as of now, you understand that this lower 128 bit RAM, right, this is accessed by direct and indirect addressing mode, whereas the special function register can be accessed by direct addressing, right? And apart from this SFR, that is special function register, the upper 128 bit address, the 128 bit can be accessed only by indirect addressing. Only SFR, that is special function register, can be accessed using direct addressing mode here. Apart from that, the remaining part, right, remaining memory location can be accessed indirectly in the upper 128 bit RAM. Clear? This is about the memory organization of RAM. And you can see here, we know that the RAM can also be extended up to 64 kilobyte, right? And the data range from 000 to FFFH, right? This is the external 64 kilobyte RAM, right? Which can be accessed using DPTR. We have seen this data pointer in architecture, right? And 8051 also provides the access to the external memory. That is, it provides a read and as well as write operation, and also the control signal can be derived from the address line, right? And this is the overall picture about the internal RAM, right? You can see here the 128 kilobyte RAM, right? The internal RAM that is accessed by using direct and indirect addressing. The range starts from 00 to 7H. Similarly, the upper 128 bit RAM, right, that is allocated for special function register. Its location is from 80H to F of H, right? And it can be accessed only through direct addressing only. And this is the overall split up about the RAM location, right? We have already seen this. That is, you can see here, right? This is the lower 128 bit RAM, where it is separated as general purpose register, right? Bit addressable and register banks, right? And this can be accessed using direct and indirect addressing. And the upper 128 bit, it is given for special function register, where it can be accessed only through direct addressing only, right? And apart from it, we also have external data. That is, whenever the designer want to use an external RAM, he can also go use external RAM, starts with a memory location of 0000 to FFFH, right? The maximum of 64 kilobyte of external RAM, right? So this is about the RAM location. Now we will see about the memory allocation for each and every register, right? I have already said that we have 32-bit register banks, 32 kilobytes. It's split into 32 KB, and this is 16 KB, and this is 80 KB, right? And you can see here the memory allocation starts from 00, 01, 02, 03, 04, 05, 06, 07, and then 08, 09, and A. You know that hexadecimal representation, how it works, right? Similarly, you can see A, B, C, D, E, F, and after that it starts with 10, and again it reaches 19, and then it's 1A, 1F, and then after 1F it will be 20, right? 20, and then it starts from 21, 22, 23. Similarly, it continues till 2F, right? And then it starts with 30. Like that it goes on, right? Like normal hexadecimal representation, how you represent the normal hexadecimal representation. And we know that it is an 8-bit register. In 8051, most of the registers are 8051. So all the registered banks, you can see it starts from 00 to 07. This is 8 bits, right? And similarly, this is 8. And totally you will have 32 kilobyte, right? And this registered banks can be selected by using PSW, right? That is bank 0, bank 1, bank 2, bank 3. About those 2 bits in the PSW, it select the registered banks, correct? And similarly, bit addressable, I have already said what is bit addressable, and the memory allocation starts from 20 to 2F, right? And it is 16 kilobyte, right? And the remaining 80 kilobyte is for general purpose register. This is the overall RAM split up, that is the lower 128 byte memory allocation of RAM, right? And you can see in the internal RAM location the same thing, bank 0, bank 1, bank 2, bank 3, right? And the byte address you can see here, right? And similarly, this is 16-bit addressable, and this is general purpose registers, right? And this is the upper 128-bit RAM, right, where the memory location starts from 80H to FFH, and this is allocated for special function register, right? And you can see here, this is we have 3 different registers. One is the register banks, right? And another one is bit addressable register. Another one is special function register. We have already seen this. Register banks, bank 0, bank 1, bank 2, bank 3, right? Where you can see this PSW pin that determines which, depending upon the value of PSW 2 pins, right? It determines which register banks will be selected, right? And the memory location starts from 00 to 1F, right? Similarly, this is 16-bit addressable memory, that is bit addressable memory, where you can see bit addressable, right? Bit addressable in the sense you can see this is the byte address and these are the bit address, right? We can also access each and every location separately, that is bit addressable, right? And similarly, special function register, which is the upper 128-bit, right? Special function registers, you have accumulator, right? Data pointer, all those comes under special function register, right? And it starts from 80H to FFH. So this is about the complete RAM memory organization. Now we'll see about read-only memory, right? So when it comes to read-only memory, right, we know that it has 4 kilobytes of internal ROM. It has 4 kilobytes of internal ROM, and this can be extended to it can be extended to 64 kilobyte of external ROM as well, right? And if it is 4 kilobytes, right, you can see it ranges from 0000 to 0FFH, right? Whereas the external memory, you can see the difference here, it extends up to 0FFH, whereas in external memory, the complete memory access, that is 0000 to FFFH, it can be accessed, right? And depending upon the P signal, right, P sense signal, right, we have already explained what is P sense signal in architecture, right? So if depending upon the P sense signal, we can able to distinguish whether the ROM, we use this internal RAM or external RAM, right? So P sense signal is used to access the external memory, right? So it determines whether we are using the internal ROM or external ROM. Now we'll see how the memory organization in RAM, right? And in memory organization in RAM, as I said, you will have internal memory, right? Internal memory of 4 kilobyte, and the complete external memory, you can see this is the complete external memory. The complete external memory is 64 kilobyte, right? And if we have internal 4 kilobyte, then this internal plus 60 external, so it will make 64 KB, right? Now as I said, the EA pin, right? This EA pin tells you whether we are using the internal ROM or external ROM. Whenever this is set to 1, whenever the EA pin set to 1, right, as I said, the PSEN determines whether the internal ROM or internal ROM or external ROM. Whenever EA is set to 1, it does mean that the memory which is accessed here is internal ROM, right? So when it is internal ROM, the internal ROM ranges from 00000H to this particular 4 KB, right, to this particular location, and again it starts from 1000, right? That is, here it starts from 0FFFH, right? Plus it can also, if needed, we can also extend from this external memory, which is 4 kilobyte plus 60 kilobyte, right? And this is for internal. If EA is equal to 0, then there is no split up the complete external memory, right? That is from 0000 to FFFH, right? That can be accessed externally, right? So depending upon the EA pin, the P signal, right, tells you whether we are using the internal ROM or the external ROM, right? And now this is about the memory organization of ROM and as well as RAM using 8051, right? Now we will see input output addressing, right? We have already seen what is input output ports, what are the different ports, right? What are the dual purpose ports in pin configuration, right? Please go through that before going through this IO addressing, right? In 8051 we have 4 different ports. We know that port 0, port 1, port 2 and port 3, right? And totally we have 32 input output pins, right? We have 32 input output pins, and out of this 32 input output pin, 24 input output pins are dual purpose. What is meant by dual purpose? Dual purpose in the sense we can also configure it as an input output port, or we can also use it as an address bus or a control line, right? And out of this 24 dual purpose, right, the one port, that is port 1 will only be used for input output port. All this we have already seen, right? Now we will see how to configure a port for input output configuration, right? For input output configuration addressing, right? So here all these ports except port 0, all these ports will have the push pull resistor. I already explained what is push pull resistor, right? So only the port 0 will not be having the inbuilt push pull resistor, right? And whenever we need to set an input register, that is, any port has to be accessed for input port, it has to be set to 1, right? And if we make the pins to 0, then it will act as an output, right? So that is what explained here. Input output pin, all these circuits with the microcontroller may be connected to the pins, right, to the corresponding ports except the port 0, because it does not have the inbuilt pull-up resistor, right? And the input pin will be applied, the logic 1 will be applied to the P register, that is post register, and for input configuration the output transistor will be turned off, right? So that is why it will be acting as an input port, right? And whenever we want to configure it as an output pin, then we have to give logic 0 so that it will remains in the ground state, right? And coming to port 0 is characterized by 2 functions. One is we can configure, that is, whenever we need to use an external memory, right? Whenever you need to access the external memory of the lower byte, we go use for port 0. And similarly, port 0 does not have the pull-up resistor, right? And port 0 can be configured as an output port. That is because it will act as an open drain, right? And when it comes to input configuration, since port 0 does not have pull-up resistor, right? Whenever you give input 1, that is, if you apply logic 1 to port 0, then it will float, right? That is, the input will have unlimited input resistance, right? And that is why pull-up resistor is very, very important. And whenever we need to configure 0, then the port 0 will be acting as an output, because it will act as an open drain. By applying logical 0 to port 0, the appropriate pin will be connected to the ground 0, right? So as of now, you understand, whenever you need to configure a port for an input configuration, you have to give logic 1, and whenever you need to configure the port to an output pin, then it has to be configured with logical 0, right? That is about IO addressing, right? And apart from it, we have already seen interrupts of 8051. What is interrupt, right? I already explained it. Whenever you execute any program, that is, this is a main program. Whenever we execute any program, while executing a program, if there is any interrupt, that is, we need to address any particular issue, or we need to process another set of instruction, then that is called as interrupt, right? So that interrupt, whenever a main program is interrupted, 8051, what it will do is it will go to this interrupt program, serve that interrupt, and then come back to this main program, right? And then it will execute the main program, right? That is about interrupt. And when it comes to about 8051, I have already explained, it has 5 different interrupts. What are the 5 different interrupts? I already explained. That is, it has 2 external interrupt and 2 timer interrupt and 1 serial port interrupt, right? So totally you will have 5 interrupts, right? I have already explained that, but today we will see about how this interrupts is enabled, right? We already have interrupt enable register, right? That is EA. You can see this is the interrupt enable register, right? And here EA interrupt enable. This is the pin which enables the interrupt, right? And you can see these are the different bits where this refers to the external interrupt 0, right? I said external interrupt, you have 2 external interrupt and 2 timer interrupt and 1 serial interrupt, right? So this is external interrupt 0 and this is external interrupt 1, and this is timer interrupt 0 and timer interrupt 1, right? So this is serial interrupt 1, right? So you have 2 timer interrupt, timer 0 and timer 1, and you have 2 external interrupt, external 0 and external 1, and 1 serial interrupt, right? And whenever you want to enable any particular interrupt, that is, say for example, if this external interrupt is enabled, then EA will be enabled, right? And if it is this timer is enabled, timer interrupt is enabled, then EA will also be enabled, right? So whenever the interrupt is enabled, this bit will automatically will be enabled, right? If this bit goes to 0, then it will reset all the interrupt, right? That is interrupt enable register, right? Now I have said what is interrupt now, right? So now, as I said, you have 5 different interrupts, right? And we have to understand, say for example, there is 2 interrupts at the same time, right? Then the microcontroller has to decide which interrupt I have to serve, right? If there is 2 interrupts at the same time, right? And that can be solved by giving priority to the interrupt, right? Depending upon the priority, right, the microcontroller will serve that interrupt, right? If it has greater priority, the one which has greater priority will be served first, and then the next one will be served, right? So that is what we are going to see in interrupt priority register, right? And before seeing this interrupt priority register, you can see here, this is the bit allocation, right? So you can see this is external interrupt 0, right? This is timer 0 interrupt, this external 1 interrupt, right? And this is external 1 interrupt, and this is serial interrupt. And this bit will be enabled, this bit will enable IE0, right? This is interrupt enabled register. IE0, 1, 2, 3, 4, 5, 6, and 7. You can see these 2 are reserved purpose. I have already explained what is EA, right? And whenever this interrupt is enabled, right, the corresponding pin, the corresponding bit will be enabled, right? If it is external interrupt, then this bit will be enabled. If it is timer 0, then this bit will be enabled, like that, right? Now, you will understand what is priority register. Priority register, it will give the priority for the interrupt, right? When two interrupts, right, that is 0, you have two priorities here, 0 and 1, right? So that is low priority 0 and high priority 1, right? Right. If two interrupts which comes in is different, that is one is low priority and high priority, then definitely interrupt priority register will give importance to this high register, right? High priority register, right? If not, if both the interrupts are high, if both the interrupts are high or both the interrupts are low, right, then what will happen? Then the priority register, it will give priority based upon polling, right? What is polling here? As of now, you understand polling is nothing but in the same order. You can see here, this is the original priority. If it is low priority and high priority, definitely what it will do is it will give the preference to the higher priority. If it is same priority, then it goes for polling method. What is polling method? Polling method is nothing but you can see here, this is the first bit, this is second bit, third bit, fourth bit, fifth bit, right? So this interrupt, this has the higher priority, this has the second priority, third priority, fourth priority, and fifth priority. So if both the things are high, then depending upon this bit values, depending upon this priority, right, it will give access to that particular interrupt, right? So that is about interrupt priority register. Whatever I said, that is what explained here, right? Hope you understand it, right? So once again, this is the same thing which we saw, right? That is the different interrupts and different pins, right? And you can see the bit values, bit 0, bit 1, bit 2, bit 3, bit 4, bit 5, right? So say for example, this is external interrupt 0 and external interrupt 1, right? If both this, no, it has 0 and this has 1, okay. Let us say that this external interrupt 0 and this timer interrupt, right, happens at the same time, right? Both have 0 priority, right? Then definitely this one will be given priority because it will go for polling method, that is the first bit will be given the higher priority. Based upon this bit position, it will be given the higher priority, right? Hope you understand what is interrupt and how the priority is given, right? And the last thing is we have to know about stack in 8051, right? Stack is nothing but a temporary registers, right? It can be called as a stack, that is a group of registers that is used for temporary access, right? We have stack pointer to access this register, and it is 8-bit wide, right? And it can be having the values from 00 to FFH, right? And we use push and as well as pop operation, push and pop operation whenever we need to input any data to the stack and remove any particular data from the stack. For inputting data, we use push operation, and for removing the data from the stack, we will use pop operation, right? So today what we have seen is we have seen memory organization of 8051, and we have seen how the interrupts are given priority, right? And we have also seen about stack pointer, right? Hope this video will be very useful for you. Thank you, my dear students.
Thank you, students. Thank you for watching. கண்டிப்பாக இந்த வீடியோ உங்களுக்கு எல்லாருக்கும் ரொம்ப யூஸ்ஃபுல்லாக இருக்கும் நம்புகிறேன். Subscribe Passionate Professor and keep learning. Thank you very much.